So in this particular talk, I'm going to talk about our project in what we call high confidence physical systems. I already described briefly what we think these physical systems are. One of the things that we need to highlight here is that typically these cyber-physical systems are safety critical systems. So it means we need to prove properties about them, and we need to be sure about the properties that we are talking about. That's why, for instance, in the talks that you have heard so far, we talk about sound techniques, meaning techniques that when we say something, a property holds, it will be there, right? So that's actually what we go after here. So we focus on three areas. One is timing. The second is, I will say, the logic or the functionality. And finally, the coordination. Notice that we have discussed before that cyber-physical systems, yes, they can be a single system, a single car, vehicle. But now, more than ever, when we go forward into vehicles and we talk about UAVs, we need to talk about coordination between UAVs, right? The challenge in this coordination is that as the complexity of systems grow and as we face uncertainty, then kind of very deterministic models do not work. So we need to add a way to represent this uncertainty, and we go for a probabilistic way to model this uncertainty. So as just guiding a scenario, think about, again, UAVs. So when we talk about multiple UAVs coordinating, we need to talk about the timing. For instance, we need to ensure that they will not collide. It means they need to react on time before they collide. We need to talk about the functionality, for instance, the absence of deadlocks and race conditions. Excuse me. And we also need to talk about the coordination, meaning, of course, they have a mission. They need to, for instance, have a coverage. So this coverage actually need to be verified. So how do we do that? So let me start with the first one. When we talk about timing and real-time scheduling in particular, that is my area, we are facing kind of the next generation of problems, if you will. So I mean, in the past, with single-core scheduling, things were well developed, but suddenly somebody came with the idea of having multicore, and then say, yeah, that looks like a nice idea. And then suddenly we start discovering that there are some really bad issues with multicore in real time. And by really bad issues, meaning that the shared hardware that we have actually creates delays on one another. I mean, tasks running on one core can be delayed by another task running another core because of the shared hardware, right? Shared memory, shared cache. The other thing that is obvious is that we need to do parallelization in order to actually take advantage of having multiple cores. So parallelization means that we need to create a new scheduling algorithm that takes into account the parallelization, right? So those are the different challenges that we face. So what we had to do first is to say, well, let's create a scheduling algorithm to do parallelization. So we did that, we created that. We created what we call the stage parallelized execution model to be able to kind of test the timing response, the response time, and verify that they meet the deadline. And we created a test for this. This is actually, I will say, as efficient or the most efficient one that is out there at this point in time. But once we have that, then we need to move to the next challenge. And the next challenge is about having shared hardware, right? So of course, every core will have their own private cache, but they also have shared cache. And the shared cache actually starts to be a problem. But beyond the shared cache, we also have a memory bus that we need to share. And then finally, the main memory. So all of these are shared. There are sort of a few good news. For instance, we can say, well, actually the cache is a collection of banks. So maybe we have some partitioning that we can take advantage of. And actually that's what we go after. We go after the partition that is already in the hardware and ways to exploit this. But how bad can this be? Well, we run experiments on benchmarks, parsec benchmark, and we observe that the interference we can get out in a 4-core can be as bad that it could create a 12x increase in the execution time in some of these benchmarks. You can see that it's not in all of them, but some of them will be very sensitive. So I mean, 12x is really, really bad, right? So we need to do something about it. In particular, I would say some contractors have reported at least 3 to 4x increase in the execution time, which is still bad. So it means we need to really go after this. So what do? I already described that we have some partitioning in hardware, banks in particular. So what we do is use a technique called coloring. It means we have a way to use virtual memory to allocate different pages of memory, of the virtual memory, to different areas of the memory, or in particular, banks. So if they go to different banks, we call it that they have different color because they do not interfere with each other, right? Notice that what we are able to do is we break the interference within a bank, but there are additional interference we need to take into account. So then what do we do to take care of this interference? So think about a task that is running in one core, right? And then it's accessing memory. So one of the things we need to verify for timing is that the response time, the completion time, is before the deadline, right? So it's a very simple test to do. If it's running by itself, it's only the execution time. But if that guy is running along with another thread that has higher priority, actually this can preempt, can interrupt the current task, and will delay the execution time. So we need to take into account that delay, right? So it will extend the execution time. If we have now also a task running in another core that is accessing the same memory that I'm accessing, that will be yet another delay. So that's another delay that we need to take into account for the response time. And of course, we need to develop these mathematics to do that. One for the task running on the same core, and for the task running on other cores accessing the same memory, right? So I mean, this, as you can see, the equation is a little bit complex because there's a lot of details I'm not showing, but there's a lot of details that I will be willing to talk to you if you have the time and are willing to go over it. So what kind of results we get? So once we get perfect partition, if we get perfect partitioning, we can really go very close to the normalized execution time. 100 is the normal execution time. A little bit over is exactly what the kind of interference we are getting in a normal circumstance, a normal workload with a perfect partition. Obviously, part of the problem is that, well, this is what we focus this year, but we have been working also in cache partitioning. So when we do this cache partition, remember we do this coloring, right? But if we put together cache coloring and bank coloring, sometimes the colors that do not, let's say, interact in cache will interact in banks. So there is a conflict. We need to do a coordinated allocation of banks and cache colors. And this actually is due to the number of bits, or the bits in particular in the address space that are used for banks and cache, that creates what we call a memory grid, a memory that we can classify in bank colors and cache colors. And here is where we can see that some of these two cache colors will not interact, but the two bank colors will interact. So we need to find out what are actually the allocation that will really prevent the intersections and the interactions that we are trying to prevent. We created, of course, an allocation algorithm for this. And we use a couple of techniques, mixed integer linear programming and abstract to go after this. Just to present the quick results, we can see that in this case, we were able to reduce significantly between the non-coordinated and the coordinated allocation, this execution time. Right? We put all of this together. Remember, we're saying we need parallelized task, we need bank partitioning, we need cache partitioning. We put everything together with a mixed integer linear programming approach. And we created a new approach to do scheduling of a parallelized task with cache coloring, with bank coloring to get the final result, right? This was already submitted for just recently. Let me switch to task 2. In task 2, obviously, as I described before, we go after the functional verification. We do this for periodic tasks. I guess Sagar and Ari has already presented a little bit of this sequentialization idea to say we put a collection of tasks that run independently, merge them together, and in that merging, actually what we do is produce a sequential program that we can verify. So this year, in this particular project, we were able to get 2 improvements, if you will. One, in the software model checking we do in this program, where we combine under and over approximation together. And for the sequentialization, actually, what we incorporated was memory consistency rules, right? So how is this under and over approximation? So an over approximation basically is a model of the system that has more behavior than the system itself. Obviously, once we verify the model, we can find out that there is a counterexample, but we don't really know if that really exists in the system, so we need to refine it. So we need to refine this over approximation to reduce the behaviors, try to find out if the counterexample really exists. So we do this refinement loop. Over approximation is a little bit the opposite. It means we create a model that has less behavior than the real system. And we say, well, there is no counterexample. We can have a proof. But the proof, we don't know really if it exists. We need to expand the behavior to really see whether it exists. So these two are combined, these two techniques, to really narrow down the, I would say, the behavior to find out whether we really have a counterexample or a proof. Right? Obviously, part of the good things that we have over this is that it's faster than other tasks. For instance, in over 100 tests that we did, over 500, we were better than the other cases. Now, for the sequentialization, the improvement was adding the consistency rules and putting this into what we call a verification condition. This verification condition is actually expressed in what is called an SMT language that can be used with an SMT solver that actually will tell us whether we have a bug with the proper counterexample or whether the system is okay. This new technique with these new consistent rules and the expression in SMT allows us to have an improvement of 7 times better than the previous way we were doing things. Finally, let me move to task 3. In task 3, actually, we focus on these multi-robots. And we are trying to capture the probability of meeting particular properties. As an example, think of a robot that moves from a base station looking for mines, and it will try to return back to base to tell there is a mine or not, right? Obviously, we will have multiple of these robots, and then once they discover the mine, it will return and inform the others, hey, there was a mine, let's go back to base to inform that the mine is in a particular position. Obviously, because the robots are not deterministic, have some probabilistic behavior, we need to model this in a probabilistic manner, if you will. Typical properties that we go after is to say what is the probability of finding a mine and returning to base to inform of the mine, and what is the probability of, or what is the number of robots that are expected to go back to base. Right? So those are kind of 2 sample properties that we verify. Communication is very deterministic within a radius, and that's it. Beyond the radius, it's not possible to see anything. And the same happens with the detection. So these are modeled as each independent robot by themselves. Ideally, we should be able to combine the robots together in a multi-robot system, in a Markov chain, send it to a Prism, our tool, and get the results. The problem in reality is that it's very difficult to create these, I would say, combined models. So what we do is take one of these and do sampling. I mean, what is the probability of missing or having this different detection of a mine if I run for 1 minute, 2 minutes, 3 minutes? So we do a sample of one of those robots. Then we put multiple of these together and create kind of the general model and send it to Prism, of course. But of course, sometimes we have errors. So what we do is, in order to accelerate this simulation, we use BREP, that is a simulator. But we also we are trying to quantify what is the error that we have in the prediction. So to do this, first of all, we try to get more behavior. doing some disturbation, probabilistic fuzzing, if you will. And then we create the new model out of this first, the simulation. We go some disturbance of the behavior probabilistically, and then we integrate the models again, send it to Prism. And of course, part of what we are trying to find out is that within a range of 90%, what we should expect, we take out the tails. How can we compare our observations with what the model is giving us? And we will see that we will have some errors that will go outside the range of what we expect. So that's expected. So we have some errors there. The same happens with the number of robots that we get out of. So we will have some errors as well. This paper was published just recently in SimPar.